In this video, we will talk about relation between Fourier transform Fourier series and discrete Fourier transform. Let us first talk about Fourier transform. Fourier transform suppose this is our real line and on this real line we consider space of sufficiently well behaved functions which are differentiable and so on, and which go to 0 in plus infinity and minus infinity directions. So in the space of such functions we have a linear operator Laplacian operator which is d square by dx square. So this is a linear operator on the space of sufficiently smooth and well behaved function on the real line, and this operator has eigenfunctions psi kx which are of the form exponential ikx. So here k can be any real number. So these are the eigenfunctions of the Laplacian, and their corresponding eigenvalues are if we act by d by dx square, act by the Laplacian on this function, then we'll get minus k square psi kx. So eigenvalues are minus k square, and these are the eigenfunctions. So these eigenfunctions form a basis in the space of sufficiently well behaved smooth functions on the real line which go to 0 sufficiently fast in the plus infinity and minus infinity directions. So if we have any such function on the real line, then such a function can be written in terms of these functions psi kx as a linear combination of these functions minus infinity to infinity. Here these are the coefficients in this linear expansion f cap k, and by convention I am here including a factor of 1 by square root 2 pi. In different conventions this factor could be different. So we are able to expand this function in this basis of eigenfunctions of the Laplacian, and these coefficients f cap k, this defines another function f cap k, the coefficients, which is called the Fourier transform of the function f, and this Fourier transform, these coefficients are given in terms of f as fx exponential minus ikx dx. So the Fourier transform on the real line is related to linear expansion of functions in the basis of eigenfunctions of the Laplacian operator. So this is our Fourier transform on the real line. Now consider, instead of real line, consider a circle and on this circle, suppose we use angle theta as our coordinate. This angle theta goes from 0 to 2 pi, and any point on this circle can be marked with an angle theta between values 0 and 2 pi. The Laplacian on this circle is d square by d theta square. So for the space of smooth functions, twice differentiable functions on the circle, this is our Laplacian operator, and this Laplacian operator has eigenfunctions psi kx. Here we have coordinate theta, so let me write it as psi k theta as exponential I k theta. So these are our eigenfunctions. The difference from the case of the real line is that here k must be an integer, and the reason that k must be an integer is that we require these functions to be smooth, and in particular we require them to be continuous. So the value of this function at theta equal to 2 pi must be same as its value at theta equal to 0, because theta equal to 0 and theta equal to 2 pi refer to the same point. So these two values must be same. So this implies k must be an integer. So our eigenfunctions of the Laplacian operator for the case of a circle are of the form exponential I k theta, where k has to be an integer. Now if f is a function, twice differentiable, well-behaved function on the circle, we can write such a function because these functions form eigenfunctions form a complete basis. We can expand such a function in terms of these eigenfunctions, and because k is an integer, so this expansion will be a infinite sum. Instead of an integral, we will have an infinite sum f cap k exponential I k theta. Again, we are introducing a conventional factor of 1 by square root of 2 pi. So this is our series, Fourier series, for the case of functions on a circle, and these coefficients f cap k are called Fourier series coefficients or Fourier transform. In this case are given as 1 by square root 2 pi 0 to 2 pi f theta exponential minus I k theta d theta. So this is how our Fourier transform appears for the case of functions on a circle, and it is called Fourier series because k are only allowed to be integers, so we have a sum instead of an integral. Now if we have a function on a finite interval, suppose we have a finite interval 0 to p, and we have some function defined on this finite interval, It is only defined in this interval. Everywhere else this function is not defined. Such function can be mapped to a function on the circle by mapping a point x in this interval to angle theta, where theta is given by 2 pi by p times x, and mapping value of this function fx at this point theta. We define on the circle, we define a function g whose value at point theta is f p upon 2 pi times theta. So this function f defined on the finite interval 0 to p defines a function g on the circle by this definition. So such function, since g is now a function defined on the circle, it can be expanded in this series, and since g is related to f by this definition, so if we do this calculation, we will be able to write f as a series in terms of exponential functions, and this expression is given as fx will be 1 by square root 2 pi sum k minus infinity to infinity f cap k exponential I 2 pi k by px, and value of f cap k will be 1 by 2 pi square root 0 to p. Here instead of 1 by 2 pi square root, we will have square root 2 pi by p fx exponential minus I 2 pi k by p x. So we have these two expressions can be derived from these expressions, these series expansions, by using the fact that g is a function on the circle, so it can be expanded in terms of these eigenfunctions of the Laplacian, and then using the fact that g is defined in terms of f by this equation. So derivation of these two equations is very simple. I'm leaving it as an exercise. So this is our Fourier series for the case of a function which is defined on a finite interval, because any such function defined on a finite interval can be mapped to a function defined on a circle. Now, in the third case of discrete Fourier transform, consider a discrete space. Specifically, consider a circle graph which has n nodes. So our graph has some number of nodes, Suppose this is 0th node, this is our 0th node. Sorry. So this is our 0th node, this is our first node, then second, and so on. This is our n minus 1th node. So this is our circle graph with n nodes, and any two consecutive nodes are linked by an edge. So these are n points which are at equidistant positions on a circle. This defines a circle graph. On such a graph, the Laplacian operator is given by the adjacency matrix A minus, because the rank of each node is 2 in this graph. Each node is connected to 2 other vertices, so this will be 2i. A is the adjacency matrix of this graph. So this is our Laplacian for this discrete space. And this Laplacian operator has eigenfunctions which are given as psi kx, psi kn. N is nth vertex, psi kn exponential I k theta n, where theta n is 2 pi by n. So for the nth vertex, if this is the nth vertex, then theta n is the angle that this vertex makes at the center. This is the angle theta n, because the angular distance between any two consecutive vertices is 2 pi by n. So the angle made by the nth vertex will be 2 pi by n times n, small n. So these are our eigenfunctions of the Laplacian for k going from 0 to n minus 1. These are our eigenfunctions. So again, since these eigenfunctions for a complete basis, for any function, any discrete function defined on these vertices, so any such function, if f is a function defined on these vertices with values f1, f0, f1, f2, and fn minus 1, this is a function defined on this discrete space, then such a function can be expanded in this basis, and this expansion looks like follows: k from 0 to n minus 1, f cap k exponential I k theta n, where theta n is 2 pi by n times small n, and f cap k, these coefficients are given as 1 by square root n, small n from 0 to n minus 1, fn exponential minus I k theta n. So this is our discrete Fourier transform, which is Fourier transform for a discrete space, which is a circle graph. So we see that Fourier transform, Fourier series and discrete Fourier transform, they're all related to each other, and the relation comes through this operator Laplacian. All these different transforms are nothing but linear expansion of functions in terms of eigenfunctions of the Laplacian operator.